Griffith. We're with the Curcumin project. We're studying curcumin complexes.
I'm Alex Czechowicz. Hi.
So this is just some basic information about our complex. We found that it does really precipitate out of solution very quickly, almost immediately, based on our HPLC data. And then we also found that it's mainly soluble in expensive polar A product solvents, of course, right? And we found that the 3-to-1, okay. So this peak right here at 6 minutes is actually our complex peak we've determined, and that's confirmed. Alex is going to talk more about it later, but we confirmed that with LCMS at NGIT, which is kind of exciting. And so then, the next slide. Okay. So actually what you can see here is 3 separate bumps, and that's because the iron is forming with the 3 separate curcuminoids. And again, like Alex had mentioned, if you guys weren't here, those are bis-dimethoxy, dimethoxy, and curcumin. So that's kind of exciting. We have on the next slide, I think it is. So this is thiocyanate. We did a little bit of like background research just to kind of find how the ratios would work for iron to curcumin. And so we used thiocyanate as that's a known 1-to-1 ratio with iron 3+. So what happens with the 1-to-1 ratio is that there's a peak at 5 minutes at about, the intensity is about 850. When you increase the thiocyanate concentration to 1 to 2, that peak goes up to about 900, and then when you increase the concentration, the ratio further to 1 to 3, that the peak actually goes up to 1300, which is why we then use the 1 to 3 ratio for curcumin and iron, and it did prove to support that information. So what that information kind of all means is that as you increase the concentration of the ligand, which the thiocyanate or the curcumin, you're actually pushing your equilibrium forward or to the right, which is exciting. It's actually forming, the complex is coming together. And what actually that kind of told us is that the process of the complexation formation is a diffusion control process. So that just means, again, like I said, that the ligand concentration is the most important factor when pushing the equilibrium to the right in an organic solvent. Okay. And these are just the 3 peaks that I told you about. This is 1-to-1, and they look. I know it looks a lot smaller. It's just because the variability was different. But so this is the 1-to-1, this is 1 to 2, and this is the 1 to 3. And you can actually also see the little iron peaks increasing.
Okay, so we've talked about UV results before in the previous semester. As we've said before, there are 3 different forms of curcuminoids. This semester we were focusing on testing them separately like we had mentioned before, and what we found was all 3 forms make the complex the same way, so it's not really necessary to test them separately, because separating them is very expensive, which is actually really made our lives a lot easier, basically. So what you see here is slowly adding 5 micrograms of iron to a curcumin solution. The black line is curcumin alone. This peak shifts and decreases, and this peak increases. This is the complex, that's the curcumin. Exactly what we want to see analytically. So it's the same for all 3, which is really good news. So we see it here, dimethoxy curcumin, same process, same pattern. Same process. And look how pretty it is. All right, so we also did UV results with the reflux. And what this shows is that it's an exothermic reaction. So green is unheated. We see the complex right here. We see the curcumin there. When we heat it, we find it goes backwards, which is bad news. You know, it shifts back in that direction, and this decreases. That means it's exothermic. But even though it's thermodynamically unfavorable to heat it, it is kinetically favorable, which means that heating it makes the molecules move around faster, so they interact with each other and make the complex faster. If you heat it too much, it falls out of solution. Really bad. Okay, so next we're talking about mass spectroscopy. We went to the NJIT lab, and Dr. Yuang Zhang helped us, which was very helpful. You know, we don't have an MS, and what this shows here, this number, 413, that's the average weight of all the curcuminoids plus 1 iron. Very good. So this is curcumin here, that's the complex. And yeah, I know that's a 1-to-1 ratio. So in MS, 1-to-1 is most stable. We couldn't see the 3-to-1. But we do have results from UV that showed that 3 to 1 or 2.7 to 1 is more stable in liquid solution. This just shows us that in the gas phase, 1 to 1 is more stable. But the most important piece of data here is that it is bonding. This is definitive proof, very important. Okay. We also use solar cells, which was really fun. So solar cells, these things here, produce voltage when you add a dye. So this, when we did curcumin by itself, and then we did the curcumin iron complex, and the curcumin by itself produced a higher voltage, which means that when it's bonding with the iron, it's losing conjugation. 1, 2, 3. Like, it's very simple, very conclusive, very quick method of testing. And before curcumin was being used, we were using, actually our friends over here were testing the raspberry dye. So curcumin is comparable in voltage, but it's much cheaper, which is really cool. Okay, so Alex is next.
Yeah, so in researching what we were going to use to start drawing some new conclusions with our data, we found that there was some bad information in certain papers, namely this example of the extinction coefficients. And to give a little background on what those are, this is an equation that we can use to find the concentration of a sample, which is important to make all sorts of quantitative conclusions. Say, it had this much concentration, it had that much concentration. One of the bad papers published had given that it was actually 30 times less, just about 30 times less of the extinction coefficient. And so imagine if you ended up putting 30 times the lemon juice that you wanted into your water. Imagine the difference, the stark difference that would give. So that was one example. And another one was that we noticed that a lot of papers would speak or discuss, there was a lot of writing on the complexes and on their formation, but there was no well-outlined procedure for that process. So yeah, those were the two main sort of gripes we had. Also, we had a microbiological contingent of this project, and we inoculated plates with 6 different types of bacteria, gram-positives and negatives, etc. We controlled for things like concentration, pH, the presence of ion, the identity of the ion, to try to see if different complexes would work. And across all of these different controls, we didn't really see the complexes outperforming pure curcumin, with the exception of one, where it was the copper ion with a high concentration of ion with Bacillus subtilis, which is one specific bacteria. So ultimately, we can't quite make any conclusions specifically about the effectiveness of the complex over the curcumin itself, but we do have a good direction forward for doing further microbiological studies. So yeah, that's about my part.
Okay, thank you very much. Any questions?